Hello everyone. In this video we'll consider an example of checking the Bode criterion, drawing the Bode plot and then applying the Bode criterion in order to determine whether the closed loop system would be stable for a given open loop, for a given plant and the controller in it. So over here we have the controller in the form of a proportional one. GCS is equal to K, and GP, the plant, is given as 1 over S times 1 plus S. And we'll consider two cases where K is equal to 1 and K is equal to 100. So we'll compare them with each other in the end. We are supposed to draw the asymptotic Bode diagram and then compute the phase margin from the drawing, taking omega c as the approximated value in the asymptotic diagram as the crossover frequency, and then we'll compare the result with MATLAB and while we draw the exact Bode diagram over there. Okay, so we can say that we have L of S as GC times GP of S, and this will give us K over S times 1 plus S. If we consider K equal to 1 for the first case, we will have L of S equal to 1 over S times 1 plus S, and therefore L J omega will be equal to 1 over J omega times 1 plus J omega. And we can decompose this into 1 over J omega times 1 over 1 plus J omega. Now we can start to draw the Bode plot for this system. We'll have the amplitude of L of J omega and phase of L of J omega. Let's say that for our x-axis, for the omegas, we'll have the logarithmic scale for omega equal to 1, 10, 100. We'll have the scaling like this. For the vertical axis, we'll have it in terms of decibel for the amplitude, so 20, 40, 60, 80, and so on and so forth. And for the phase, we'll have it in the form of either degrees or radians. Let's say this is minus pi or minus 180, and this is minus pi over 2. We have two terms here. 1 over J omega is the first term that we can consider. We know that for 1 over J omega, we have the phase being constant at minus pi over 2. Okay, I'll wait for my pen to change its color. Now it is the case. So we have the phase equal to minus pi over 2 all the time. And in terms of amplitude of 1 over J omega will be equal to 1 at omega equal to 1. And we will have the slope of minus 20 dB per decade. So at each decade, the amplitude will decrease by 20 dB. And I can kind of draw it in this way. Okay. So the drawing is not perfect, but it's a straight line crossing 0 dB at omega equal to 1, and the slope of the line is minus 20 decibel per decade. Now we have the second term, which is 1 over 1 plus J omega. For 1 over 1 plus J omega, we will have the phase starting from 0. At omega equal to 1, it will become minus pi over 4. And at infinity, it will become equal to minus pi over 2. Approximately, we can draw the phase plot for the system like this. So it's always below 0. In terms of amplitude, at omega equal to 1, it will become equal to, approximately it will be equal to 0 dB. Before that, it will be 0 dB with a slope of 0 dB per decade. And after that, we will have minus 20 decibel per decade. Okay, so this is the approximate one. And now we can combine these with each other. If we combine them, we will get the amplitude plot like this. At this point, we will have up to omega equal to 1, we will have the main contributor coming from 1 over j omega. And after that, we will have the slope of minus 40 dB per decade, as you can see here. Minus 40 decibel per decade. And then in terms of the phase, we see that it will be the phase of 1 over 1 plus j omega shifted downwards by minus pi over 2. So we will start from minus pi over 2. At omega equal to 1, we will have minus 3 pi over 4. And approximately the phase will be like this. So now that we have the Bode plot, we need to check what we are required to do. We'll take omega c as its approximated value in the asymptotic diagram, which is omega equal to 1. So this is the omega c, 1 radian per second, the gain crossover frequency, and we need to determine the phase margin referring to that value. So the phase over here will be equal to approximately minus 3 pi over 4. And we need to determine the phase margin by finding this distance at omega equal to 1. And we can see that phase margin will be equal to 180 degrees or pi plus phase of L of j omega at omega c. It will be equal to minus 180 plus 180 degrees minus 135 degrees, which will be equal to 45 degrees or pi over 4. And since phase margin is bigger than 0, we would say that the closed loop system is stable. The closed loop system is stable because the phase margin is bigger than 0. We can compare the result with MATLAB as well. I have already drawn the Bode plot for this system. The one that you see in blue indeed is what we have for k equal to 1. And now we can see that the phase margin for k equal to 1 is equal to 51 degrees, and it happens at the frequency of 0.78. So the phase margin is bigger than what we have approximated, and the crossover frequency is smaller. And I guess you know why it is the case. Because if you draw the exact, or if you compare the approximate one that we have here with the exact one, it will be, the crossover frequency will be smaller. That's because what we drew for the second term of G was the approximate one, and for that you could, maybe I can show it to you, for the 1 over 1 plus j omega, if you draw the exact one, it will be something like this. So the amplitude plot will move a little bit lower around the frequency of 1 radian per second, and as a result the crossover frequency will be smaller, which means that the phase margin will be a little bit bigger than what we have approximated. Okay, so then we need to determine if the closed loop system is Bode stable by applying the Bode criterion. It is stable because phase margin is bigger than 0 for the system. And we will plot the Bode diagram using MATLAB and directly compute the gain margin from this diagram. So if you check the approximate Bode plot over here or the actual one over here, you can see that the phase never reaches minus 180 degrees. Indeed, in the approximate one that I have drawn, the phase reaches minus 180 degrees. But if I draw the actual one, this will happen at omega equal to infinity. And as a result, the gain margin will be infinity. You can increase the gain as much as you want, but the closed loop system will not become unstable. We can also verify this by referring to the root locus plot of the system. If I draw the root locus plot for this system, you can see that for any value of k bigger than 1, even if you go towards infinity, the closed loop system will remain stable. It will not become unstable at all. We can try it for the value of k when it is equal to 100. When k becomes 100, we will have a third component here. For that component, we know that the phase will be equal to 0, and in terms of amplitude, we would need to consider the 20 decibel amplitude, and it will be indeed added to our amplitude plot. As a result, the approximate Bode plot that we may have for this system will be like this. The phase will remain the same because we are not changing the values for the phase, but in terms of the gain, it will move by 20 decibels upwards. As a result, at the frequency of 10 radian per second, instead of minus 40, we will have minus 20. At the frequency of 1, instead of 0, we will have 20 dB. So here we have minus 20 decibel per decade. And then we will shift everything by 20 decibels upwards. Approximately, the amplitude plot will be like this. Now you can see that the omega c, or the gain crossover frequency, increases. Omega c increases, it will become bigger than the previous case, and as it happens, the phase margin will decrease. Because as omega increases, the phase of the system goes towards minus 180 degrees, and as a result, the phase margin will decrease. But in terms of the gain margin, nothing will change. We will have it will be indeed similar to what we had in the previous case. Now, if you look at the exact Bode plot that we have here, we can find out the crossover frequency, which is indeed around 10 radian per second, and the phase margin, which is much smaller, it's 5.72 degrees. But still, the closed loop system will remain as a stable one. So for both values of k equal to 1 and equal to 10, the system will remain stable. The phase margin will be smaller when the gain increases, and the gain margin in both cases will be infinity, because we can increase the gain of the closed loop system and to any value, while the closed loop system doesn't become unstable. Alright, so I think that's all for this video. In the next video, we'll go through another example. Thank you for watching, and see you in the next video.